Okay, so I have another example I want to do from section 13.2. Take a moment to copy this example down. Okay, so the purpose of this example, it's not a long example, but we have, for instance, we did a problem, right, where we found the, well, what's this mean on the right? What's this mean on the right? This means the sum of two line integrals. And we did a problem where we added the sum of two line integrals. And that can be interpreted as the work that the force field does that has components P and Q. Okay, the work that that force field does in moving a particle along a path C. Okay, so whenever you are adding line integrals with respect to x and y, you are computing a work value. And incidentally, if you're adding line integrals with respect to x and y and z, as is done in example 6 in section 13.2, you are computing, again, work that a force field does in three-dimensional space in moving a particle along a path, C. So, okay, let's show why these two integrals are related. So, first of all, we start off with the definition of the, well, not definition. We know that this integral, the line integral, over the vector field f is equal to then the integral from a to b of this dot product. And I note here, of course, that dr dt is r prime of t. Therefore, dr is equal to r prime of t dt. Now, what we have to recognize is this vector field f. A vector field, of course, it's a field of vectors, and the vectors vary as you move along the xy plane. And in this case, it's a two-dimensional vector field. But of course, we're interested in the points in the xy plane that correspond to the points on the space curve. And those points, those xy coordinate points, are found when you're at a point xy on the space curve. There is a, the space curve function, the R of t that traces out the space curve has coordinates x and y, and they are functions of t. So you see, you can write this f of rt like you see here. And then the derivative of r prime of t, that vector, the vector function r prime of t, has components x prime of t, y prime of t. You do the dot product, and that gets you here. The integral from a to b of p times x prime of t plus q times y prime of t dt. So this example here that I have made up, it hopefully it connects a lot of things. Now the integral of a sum is the sum of the integrals. But because dx dt is x prime of t, x prime of t dt is therefore dx. And similarly, dy dt is y prime of t, so y prime of t dt is dy. And so you end up getting then that the work is actually equal to the sum of two line integrals, one with respect to x and one with respect to y. And if you were computing work in 3 dimensions that a vector field does in moving a particle along a path, it would be the sum, it would be equivalent to the sum of 3 line integrals, with one with respect to x, one with respect to y, and one with respect to z. So this is just it's an important idea, and you know, want to make sure that what you're doing makes some sense, and you get an intuitive feel for what you're doing here. All right, are there any questions on that? On that example? Okay. Hopefully it'll help you feel comfortable with the notation. Lexi says she likes this sort of example. I completely understand that because it just helps you get comfortable with the notation, and but I'm very happy to hear that, Lexi. Excellent, excellent. Okay, I will stop the recording then.